So the last day I introduced you to the idea of quantum mechanics, quantum theory. Quantum mechanics is actually just the name that goes along with the physics that deals with this tiny, the world of the tiny. And that's what quantum mechanics is. It is a theory and then eventually a mathematical construct, just like any physics is. We mathematically attempt to explain what we observe. And it's a mathematical construct that if we put in our laws of physics along with the new ideas of quantum mechanics, and then we put them in to a specific situation where we're dealing with electrons being attracted to protons in orbit, and you do the mathematics, you get these neat things that come out mathematically that we call now orbitals, all right? An orbital, again, is just a name that chemists have applied to these three-dimensional shapes where 95% of the time we have a probability of finding the electron. Because remember, we have these things like what is called the Heisenberg uncertainty principle. It's impossible to know exactly where an electron is and to know its speed to absolute certainty. There's always an uncertainty when it comes to locating electrons. And that has to do with these probability wave functions. What great words we get to use in quantum mechanics. Probability wave functions. That's cool stuff. Anyway, so we get these shapes, we get these things, and we call them orbitals just because Bohr called the location he found electrons orbits, because they imagined that they had to move around in this nice circular pattern, but we now know that that's not the case. We don't even worry about how they move. We don't even care about how they move. All we care about is that we will most likely find an electron in this region of space defined by this shape. And what we want to do today is, again, talk about the shapes and talk about where these shapes come from. And then we want to talk also, eventually, how we order these shapes in terms of energy, starting from their lowest energy going up to higher energies. And I'm looking at your Monday morning eyes, and you're all staring at that poster. You can't take your eyes off of it. It's got such cool shapes on it. And that's good. Those shapes are computer-generated orbitals, the exact orbitals that we're going to talk about here today. So I'll be making reference to this page. And they're beautiful, aren't they? They're like flowers, except it's chemistry, which is just cooler than just flowers. Because that's just like environment and going outside, and this is better. Trust me, it's much better. Okay, so I described to you also the last day that there was this mathematics that they used, this mathematical construct that in the end, chemists, physicists obtained this huge equation, and I've calculated that one. It's a crazy equation. Don't ask me how to do it now because I can't remember. But it's this big equation that has 4 variables in it. And as you change the variables, that equation, which literally can be graphed and therefore get you a shape on a graph, and that's what these are. These are essentially just shapes on a graph that are graphed after these numbers are put into them, all right? And these numbers define these orbitals. And the thing that we need to know as chemists is orbitals are where the electrons go, and that's what we need to know. So let's talk about these quantum numbers. First, I have that exact poster put up on the screen so as I'm videotaping it, people can see it, or people are away, that type of thing. And you'll notice it looks a lot like the periodic table. And that's because we now know that the way we fill these orbitals with electrons is what truly defines the shape of our periodic table. You may notice also that it isn't exactly like the periodic table, because our true periodic table has 2 rows in that first piece, but this only has 1. And our true periodic table has 6, rows in that part over here, and there's only 3. And that center part has 10 steps, and this center part only has 5. You'll notice it's exactly half. And that's because each of these orbitals can hold 2 electrons. So our first 2 rows are determined by whether there's one electron in this orbital or two electrons in this orbital. All right? So it has everything to do with the orbitals. All right, let's talk about the numbers, and then we'll make reference to this sheet. So quantum numbers, write down the first bullet and the last bullet. Don't write the center two bullets. Not nearly as important. So the quantum numbers define the size and shape of the orbitals, and it also describes the electrons that make up the orbitals. Second bullet, not so nearly important to write. Chemists use these numbers to define the state or location of an electron. We're really defining where we can find the electrons. Sometimes it's called simply the state. And when we say state, we obviously don't mean solid, liquid, and gas. We mean its energy state. The term state in physics is sometimes used to describe all of the properties of that thing, right? If you had a projectile flying through the air, you'd have so much gravitational potential energy, you'd have so much kinetic energy. That would be its state, right? Its total energy. So we sometimes use the term state to describe its properties, right? So in this case, the quantum numbers describe the properties of the electrons, what state it's in, where it is in terms of its energy value. You can think of these quantum numbers as the address of the electron. So it's where we would find the electron, you know, if we were to go looking for it, 95% of the time, which is good enough. A very important statement at the end: no two electrons can have the same form quantum numbers within the same atom. In other words, you can't describe the two electrons as being in the exact same state. In terms of an analogy, in terms of physics that we understand, like the projectile thing, you know, you could know its potential energy and its kinetic energy, and its position would also define its state. If you were to put another projectile and give it the exact same state, you would literally have to superimpose that projectile on top of the other one, literally having it occupy the same space at the same time. And we know that matter can't do that. You can't overlap two pieces of matter to be right on top of each other. Matter cannot do that. That's not a property of matter. You can't put two things at the same point in space at the same time. It just doesn't work. One will bump out the other. That's the same thing with electrons. You can't put two electrons in the same region of space, like right on top of each other at the same time. So that's the same type idea, that they can't be at the exact same spot at the same time. Okay, let's now define these quantum numbers. The first quantum number is very simple. We call it the principal quantum number. And it essentially defines the energy level. This is the same quantum number that Bohr proposed. So the first orbit, n equals 1. First level. The second orbit, n equals 2. Just like with Bohr's energy levels, the first orbit can hold 2 electrons. The second orbit can hold 8. In a moment, I'm going to introduce you to the next quantum number, which defines the sub-levels There's subdivisions. But we still see that here even with this orbital diagram. The first one, you'll notice there isn't a picture over here. That's because that's the first energy level, the first, not orbit, but orbital. In the second energy level, you'll notice 1, 2, 3, 4. There's 4 orbitals. Now we're going to look at the sublevels. So just like Bohr, the first energy level, the second energy level, the third energy level, the fourth energy level, et cetera, et cetera. Okay? So it's exactly the same as Bohr's. Let's now define the sublevels. Now I put a picture here just to reference it, but again, first energy level, second energy level, third energy level, et cetera, et cetera. Let's now talk about the secondary quantum number. Now, different levels of textbooks will name this differently. We call it the secondary quantum number to keep it simple, the second one, right? Sometimes it's called the azimuthal quantum number, has to do with its shape, all right? Has to do with the way it's physically represented. I'm going to jump ahead here. I just want to see what my next slide looks like. Yep, good. Now this is a script L right here. What you're seeing right there is a script L. So it's like it's written. That's the kind of, it comes from a letter L, right? And that's to distinguish it from a number 1. That's why, so that's why we write it. You will notice that the values of L depend on the value of N. So we've got to look back to see what energy level we're in to determine the values of L. So let me just go over some examples here. You can write this underneath here. Example, if N equals 1, if we're dealing with the first energy level, all right, then the value of L, which is dependent on N, is equal to 0 all the way up to N minus 1 in integer units. So 0, 1, 2, 3. And they're just numbers at this point. So if N is equal to 1, what's N minus 1? Good Monday morning question here for you. I think you can handle this one. If N is equal to 1, what is N minus 1? Christian, congratulations, 0. That's good. This is Monday morning, folks. That's a great move. So that means for the first energy level, L can be 0 all the way up to N minus 1. The only possible value for L is 0. In other words, there's only one possible value for L. What this tells us is that there is only one sublevel type in the first energy level. There it is on my picture. There, that's the only orbital that's in the first energy level. It's the only one that exists. If N equals 2, what's the value of N minus 1? If N is equal to 2, what's N minus 1? Christian? It's 1. He's on fire this Monday morning. It's fabulous. That means that the possible values for L are 0 as well and 1. There are 2 types of subshells in the second energy level. And on my picture, I hope you can see it. There's one, there's the first one, and there's the second type. All right? Yep.
Does that mean that L has to be a whole number?
Yes, it's an integer as well. All right? And if I were mathy, I could say L is, how do I do that? How do I say L is an integer in math? How do I write that? Some symbol, and then it's got, is it an I or is it an R, or real numbers? You know what I'm talking about, you mathy people? Come on, Lauren, you know what I'm talking about. You're just hiding your mathiness over there. I don't really care, it's okay. But you know what I'm talking about, how they say is all integers. Yes, has to be integers. So one last one just to kind of illustrate it. If N is equal to 3, what are my possible values of L? I won't even make you do the n minus 1. What are the possible values for L? Christian, I think you understand. I'm going to go to someone else. That's good questioning. Yes, Elena. 0, 1, and 2. And that means there are 3 types of orbitals in the third energy level. Okay? All right? And we could continue on for the different energy levels. You get the idea. Now, I've already introduced you to another way in which we write this sub-level designation. If L is equal to 0, we don't like to use the mathy stuff as the chemist because we really don't care about the mathematical equation. So we want to be able to describe these sublevels, and if L is equal to 0, we have s orbitals. You do need to write this down. Very important stuff. Now, I very quickly introduced you to the shapes of the orbitals. I'm going to write some of them down here again, just very quickly. But that's what this little orbitron gallery that I found online describes. If L is equal to 0, we call them s orbitals, and they're all spherical. S orbitals have a 3-dimensional shape of a sphere. And you can see here, there's all my s orbitals on that orbitron picture. If L is equal to 1, we call them p orbitals, and they look like the dumbbells. Did I show you the dumbbells the last day? So here they look like dumbbells. These dumbbells are just turned perpendicular to each other, but they all have this dumbbell shape. Those are p orbitals. If L is equal to 2, then they're d orbitals, and these are the d orbitals in here in the middle, and here you can see it. They almost look like clover leaves. These clover leaves are turned in different directions to each other, and then there's one odd-looking d orbital that looks like a p orbital with like a hula hoop around it. So we're not going to worry about that one. I'm going to just draw the clover leaf guy. Oh, that was horrendous. I don't know what happened to my computer there. Oh, my goodness. Whoa. All right. That's the worst d orbital ever in the history of d orbitals, but you get the idea. It's like a clover leaf. And you'll notice they get more complicated as you go. You've got this nice sphere, then you've got this thing with 2 lobes, then you've got this thing with 4 lobes. And F, I'm not even going to bother with, but way down at the bottom here, you can see some images of the F orbitals. And again, here we've got like a P with 2 hula hoops. And then we've got, I don't even know if you call that a clover. You don't call it. It would be like a 6-leaf clover or something like that. More lobes to it. Don't worry about drawing it. You don't have to worry about that stuff. Yep. S, P, D, and F, yes. We can continue putting in as many values for L as we would like, right? Because N can go up to infinity, which means L can go up to infinity. And that's just part of the mathematical construct, right? Because the mathematical construct can actually be extended to however large numbers we want. It turns out that in nature, we only find elements that need to use the F orbitals. We only have actual elements that have been discovered that use F orbitals, so there's no need to worry about the others. And there are letter designations. After F, they use the alphabet because they realized mathematically that you could go on forever. And S, P, D, and F actually come from historical names that came from their spectra. Sharp. D is diffuse. Talks about the way the lines in the spectra would spread out. Right? That's what was called the Zeeman effect. I don't know if you recall the little note on the Zeeman effect. All right? So that's where those names come from. So if you wanted an L for 4, it's a G, and then an H, and then an I, and then a J. But nobody cares about those because we don't have atoms that hold that many electrons anyway. Okay? So we're only worried about S, P, D, and F in this course. All right. Let's now talk about, and there's the pictures, right? There's the S guys. There's the P guys, there's the D guys, and there are the F guys. Excellent. 2 more quantum numbers. The magnetic quantum number. indicates the orientation in space. So it describes where you'd find them with respect to each other. This is actually the one that presented itself with the Zeeman effect, because Zeeman put a magnetic field around the atoms, looked at the spectrum, and the lines would split. And they split into, well, you can't split into one. Some lines didn't split. Other lines split into 3. Other lines split into 5. And that has to do with the magnetic quantum number. That's why it's called a magnetic quantum number, because they presented themselves when the atoms were placed under a strong magnetic field. So now, each of the L's have then a value that's called an ML. So now we've got N, which determines the L's, and then each L gets a group of numbers called M subscript L. And again, I'm just going to jump ahead. I want to look at what my next slide is. Yep, good. Again, what I'm doing today, I just want, as you're writing, I just want you to kind of think about what I'm doing, because we get kind of lost sometimes in all of these numbers. What we're doing is we're defining the orbitals, which is the place the electrons are found. So it's like we're building an empty atom. It's like we're building, and I'm going to talk about this tomorrow. Sometimes when we talk about filling the electrons into those orbitals, we always use a dorm room analogy. Like you've got an empty dorm room and you've got students coming in and you're filling the dorm room. So it's like we're building the empty structure where we're going to be placing the electrons tomorrow, and then we can then look at the atoms themselves. So we're just building the structure on where the electrons can go. Electrons go into orbitals, and this quantum number here defines the individual orbitals. The first quantum number was the energy level. The second quantum number told us the types of subshells. Now the third quantum number, they tell us the orbitals. In our analogy, the energy level would be the floor on which we're building the dormitory, what floor it's on. The second quantum number would be like the type of room, whether you got the cheap little room or you got the good room, right? And then the third one are each individual room, right? So the type of room you could have, and then now how many of those individual rooms are we talking about? So we're to the point where we're almost done building our dormitory. This tells us how many of each type of room there is. So if L equals 0, and again, we're dealing with all integers. I just didn't know how to express that. We're waiting on Lauren for that information, but anyway. If L equals 0, ML is -0, integer steps up to +0. Look at what I just said there. That's funny. Which is exactly the true statement. -L, integer steps up to +L. And if L is equal to 0, then ML can only be equal to 0. Because if I've got -0 and the +0, it's only 0. It's the only value. What does this state? This means that there's only one S-type orbital. Only one S-type orbital. All right? So if I'm dealing with L equals 0, it means it's an S-type, and there's only one. Only, always. You can see that on the orbitron picture. In this S row, there's only one type. Now, as we move from one level to another, we get this alternating color. These are called nodes. We are not going to worry about that. All I want you to worry about is the shape. They're all spherical, and there's only one. If L equals 1, now we're talking about p-type orbitals. Again, it goes from -L, integer steps, up to +L, that means I have values of -1, 0, and +1. Which means when you have a p-type orbital, there are 3 of them. 3 p-type orbitals. It means in our dormitory analogy, on the 2nd floor, there's an S-type room and 3 p-type rooms, with a total of 4 rooms. Okay? They all have the dumbbell shape, and what these numbers represent in physical reality is that we've got something that we could call, in this case, up and down the p subscript y. We can have one that goes on the x-axis, the p subscript x. And now my attempt to draw a 3rd dimension coming out the board, here it comes out in front, and then it kind of goes in behind and hides in behind there. This is coming out of the board. This is p subscript z. So what it represents is that there's 3 p-type orbitals, and they orient themselves perpendicular to each other in x, y, z space. Okay? And that's what then we perceive in reality. This is the mathematical construct. We graph it. We get the 3 p-type orbitals. And there you can see it here. So here's the one that's up and down. You can call that the y. Here you can call that the x. And here's the one that's coming out of the board for us. All right? And if L equals 2, what are the possible values for ML? Christian? Which means I have 5, and what do we call these types of orbitals if the L is 2? Christian? Yeah, we got D-type orbitals. So we say that there's a D subshell, and there's 5 orbitals in the D subshell. All right? And I'm not going to draw them all. All right, actually, I'll advance the slide here because I don't think I'm going to deal with, I do have F because we are dealing with the Fs. What's the possible values for ML? I think Christian's got it. Jess must have it. She's yawning back there. What are my possible values? -3, -2, -1, 0, 1, 2, 3. Which means we have 7 F-type orbitals. Okay? And I'm not even going to try to draw those. Because I do have, again, that orbitron, so I can refer to that. So you can see there's my S-type orbitals, and there's always only 1. These are my P-type orbitals here, and there's always only 3. Don't worry so much about when we get down to here. You'll notice we've got this alternating colors. That has to do with the mathematics of it. We get what are called nodes. You'll learn about that in 4th year quantum mechanics when you all take it because you know you love this stuff. But right now, don't worry about it. All you need to worry about is the fact that all the S's are spheres. All the P's fundamentally are still dumbbells, right? We can imagine that fundamentally still as being a dumbbell. Okay, and then there's our D block, our D group. You can see them in there, and then down here are the Fs. All right, and again, you'll notice 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. Okay, one more quantum number, and the quantum number that we have here last, it's called the spin quantum number. It's called M subscript S because it was also discovered by a magnetic field. It describes the spin of the electrons. It turns out that electrons spin on an axis, just like the Earth spins on an axis, giving us our days. And the spin is either clockwise or counterclockwise. It's either, right-hand twist or a left-hand twist. In the big giant mathematical equation that describes these things, it's represented by only two possible values, spin plus 1/2 or spin minus 1/2. The value of 1/2 comes from the fact that it's called a fermion, and if you want to get into particle physics, there's all kinds of books and websites you can read about that, but that's where that 1/2 comes from. Not a big deal. And this spin quantum number, if we're talking about dormitories, represents the two possible beds that are found in every dorm room, right? You and your roommate. So you've got only a location for one and then two people in the room. In this case, in each orbital, you've only got room for 1 and 2 electrons, and they have to be spinning in opposite directions. All right? And that's not located on this picture. You can't see the electrons in here. You can't see their spin. It's just that they're there. There's two possible electrons that can go in each and every one of these little spots on this orbitron picture. I'll bring it back up. So 2 can go into here, and 2 can go into here, and 2 can go into there, and 2 can go into there, and 2 can go into there. All right? And sometimes with the lobes, students get thinking, oh, of course 2 can go into there. Look, there's a little space up here, and there's a little space down here. That's nice. That has nothing to do with anything. They could be both on one side in one of the lobes. They could be both right beside each other. They could be both occupying the other side, the other spaces. We don't really care about where the electrons are. We just know that they're in there somewhere. And we don't really care exactly where they are. All right? So it's not that they always spread out and exist in opposite spaces. They just exist in that space. Even with the Ds, with all these extra lobes, only 2 electrons can go in that space. All right? That'd be like the deluxe room. They've got more room, but still, only 2 can go in that. Same with the f orbitals. Each one of these f orbitals, no matter how complex they are, only 2 electrons can go in to one of those orbitals. Spin up and spin down, or spin plus 1/2, or spin minus 1/2, or counterclockwise and clockwise. However you describe it, it doesn't matter. We usually talk about it in terms of a vector analogy. It's either spinning up plus 1/2, or opposite spin is spin down. That's the easiest way for us to think about it, like one spinning on its head. Yep.
So, the D orbitals only happen at 4 seconds.
We're going to get talking about filling order tomorrow, all right? And I'm sure you can't see it, but maybe up front here, Ben, you can. Notice, I don't know if you can see that that's a 3. Can't see that? Okay, I can see it. I'm pretty close. Even though it's in the 4th row, these d orbitals actually belong to the 3rd energy level. And that has to do with the filling of the rooms. Tomorrow we're going to talk about filling order, and it doesn't fill the way we think it should. It doesn't fill as nicely as we would like it to. So that's tomorrow's question on where do we fill them. And that first row in the D's are actually in the 3rd energy level. So we've got some little extra tweaking we've got to do. Today, I'm just teaching you about the rows and how many and that type of thing. All right? You had another question you wanted to put on that?
Wondering why is the 2 rows of the X orbital and the P orbital are they in the 1st level and in the 3rd level?
Which ones? These guys? This is the 1st energy level, row 1 across. This is the 2nd energy level, row 2 across. This is the 3rd energy level, row 3 across. But these d orbitals are part of the 3rd energy level, but they end up in the 4th row. That's tomorrow's lesson. They're not ordered the way you think they would be ordered. You'd think that we would just order them 1, 2, 3, 4, as opposed to 1, 2, and then 3, and then start 4, and then go back to 3, and then finish 4. And that's exactly what we do, though. We fill a little bit of 4, and then we go back to the 3rd and fill it, and then we fill in the 4th, the rest. And so there's a little extra information that's going to come along for that. Okay? All right. Today we're just defining the rows and all that stuff. All right. Now, we're going to want this. You don't have to put all the lines, all right? But just put all the titles across your page. And this is really 100% review of what we just did. But I want to put it all out there so that you can get a sense for what we're talking about. Now, in actual fact, I just found this Orbitron picture sometime during the summer, so I didn't use it last year. But this is really what I'm doing. I'm putting together all of the possible orbitals as found in this Orbitron gallery thing. And this is a really neat representation of all the possible orbitals. So all I'm going to do now is define all of these things. Again, you don't need to put the lines. You're going to go down however far we're going to do this. But again, I'm going to just start with n equals 0. I just want to define all the possible orbitals here. N equals 0. If n equals 0, and you can flip back, does anyone remember what's the possible values for L? Christian remembers. Christian, what do you got? 0, because it has to be 0 up to n minus 1, right? That tells me that there's an s orbital. What are the possible values of ml if L is equal to 0? Yep. Oh, my Lord. It's not. If that's the case, then I've written it incorrectly on the slide, because it's not. We don't have negative ones in there. So if I've done that and I've written it that way, then I've maybe represented it incorrectly. So you may be correct absolutely mathematically, but that's not the case. You see what I'm saying? It goes up to one number lower than its L, or its n value. All right, I have to go back and look at that, see if I've maybe misrepresented it. Maybe I should write it as negative 1 plus n or something like that. Okay, possible values for ml. 0. That means there's only one. Possible values for ms. ms is the easiest one. You've only got 2 possible values, and there's no thinking involved. Pause to look back. Yep. Plus 1/2, negative 1/2. Plus or minus 1/2. That's the way I'm going to write it. See there, I've got plus or minus above each other. That represents 2 electrons. Now let me describe to you something called the letter designation of the orbital. Because L is equal to 0, what type of orbital do we call it? It's an s orbital, but I'm going to add one bit of information. Because I have an s orbital in each of the energy levels, I'm going to call this a 1s orbital. The 1 comes from, look at what I did there. Does anybody see what I did there? That's why this didn't make any sense, because you can't have n equals 0. You can't have an energy level of 0. There's our problem. There's my Monday morning gas. What's the first possible energy level? Yep. 1. Nicely done. Had a nice video going on there, and now the whole world's going to know that Sanders knows nothing about quantum numbers. That's not true. It's Monday morning, right? Don't I get Monday mornings as well? No, that's unacceptable. That's not fair. No, I'll pull one of you guys. That's not fair. All right. The 1 in the 1s represents that it comes from energy level 1, and the s in the 1s comes from the fact that it is an s-type orbital. What we want to do is eventually, when we talk about chemistry, I don't want to be talking about quantum number n equals 1, L equals 0. I want you to think of a 1s orbital. And when you think of a 1s orbital, you're going to think of the smallest spherical orbital. Okay? How many electrons can fit in that 1s orbital? How many electrons can fit in any orbital? 2. which means the total number of electrons in the first energy level is 2. We have 2 electrons in the first energy level. All right? And now that we've overcome, well, I've overcome, maybe you guys haven't, my gas here, let's keep going. You don't need to put the line underneath here, folks. I'm just doing it to kind of separate it out. You might if you want to. Let's now talk about n equals 2. Possible values for L. Yeah, Jason? You're thinking of the MLs. That's all right. 1 and 0. I'm actually going to put 0 and then 1, just because it's easier to write out and it works better order. Now, if L is equal to 0, then it has the same properties of this L is equal to 0. ML is 0. That's the only possibility. It's plus or minus a half for the electrons that go in there. And the letter designation for this is what's it going to be? Yep. It's an S. And which energy level is it in? What's the N value? So it's a 2s orbital. This is a 2s orbital. 2s orbital. It's bigger, and it's got some nodes in it, but don't worry about the nodes. It's bigger. How many electrons can fit in the 2s sublevel? There's only 2 electrons that can fit in there. That's it. Possible values for ML if L is equal to 1. Yeah, -1, 0, plus 1. -1, and you know what? I should write these all out as separate orbitals. I'm going to this time, but then when I get to the third energy level, I might not write it all out. But I should have -1, 0, plus 1. That means there are 3 p-type orbitals. Each of these can have plus or minus a half, plus or minus a half, plus or minus a half. Look at my scribble half. You guys should know my scribble halves. Should have you trained up on that. What is the letter designation for these 3 guys? Again, the energy level and the type of orbital. These are 2p orbitals. 2, and because it's a 1, it's p. These are 2p orbitals. Notice, there is no such thing as a 1p orbital. You can't just throw any quantum numbers out there. They have to be valid quantum numbers. So a 1p orbital doesn't exist. That's what gives our periodic table its shape. The first row only has 2 electrons in it because there is only a 1s orbital. There is no such thing as a 1p orbital. How many electrons can fit in these 3 1p orbitals? 2 in each. I've got 3 of them. So how many in total for all these p orbitals? Yep, 6. 2, 4, 6 can fit in the p-type orbitals. 6 electrons. How many electrons in total can go into the second energy level? 8. 8. And that's where we get our 8 across the periodic table. All right? In terms of our little orbitron picture, that's why in the second we can put 2 in there, 2 in there, 2 in there. So there are 4 orbitals in total. 4 orbitals, 2 electrons in each, 8 electrons in the second energy level. I'm going to do an n equals 3. Right, so my next slide is just a cleared view of this. 3. Possible values of L. It is repetitious, but we got to get it in our brains. And hopefully repeating. Yep, Ben. 0, 1, and 2. 0, 1, and 2. And the 0 and the 1 are just like the previous 0 and 1, except it's bigger because it's a 3. So again, I'm going to have 0. I'm going to have plus and minus a half. Letter designation. Yep. It's a 3s orbital. 2 electrons in that thing. This time for ML, I'm going to squeeze it all together. -1, 0, 1. I spread them all out last time so we could see them. But just to, make it a little more compact, we know that there was 3 orbitals there. Plus and minus a half for each of them, plus or minus a half. And I'm going to put in here a little times 3. You get the idea, I think. There's plus and minus a half in that one, plus and minus half in that one. What are those orbitals called? Yep, 3p. We're starting to see the trend. For all of you guys out there that love trends, that love, oh, is this the way? Yes. For this, you can trend this up. There is definitely a trend to this. How many electrons can fit in the 3p orbitals altogether? 6. That's true in any of the p orbitals. It's 6. They're built for 6. 2, 2, and 2. And I'm not going to spread this one out, but I think we can get the idea. What are my values for my ML if it's equal to 2? Yep. -2, -1, 0, 1, 2. And I made a mess of that, but you get the idea? Each of those can have plus or minus a half, plus or minus a half times 5. There's 5 of those in there. What are these orbitals called? What are these orbitals called? We're going to go for a rookie on this one. Rookies that are sleeping, which doesn't include you, Christian, because you're awake. Genevieve, what are these going to be called? 3D orbitals. Excellent. 3D orbitals. They are three-dimensional, but they're not. That's not what that means. Oh, okay. How many electrons will fit in all of those d orbitals? How many? 18? I don't want the total yet. You just slow down. I just want the d orbitals. Yep. 10? 2, 4, 6, 8, 10, right? And in total, all right, go ahead, Callahan, 18. 18 electrons. I think we get the idea. I don't want to do all of 4, but let's just do a little kind of summary for 4. All right. So this is my blank page. I'm done my table, but you can write this underneath your table. All right. For n equals 4. Tell me the letter designation or the name of the possible orbitals. Is it possible or possible? Possible orbitals. Tell me the possible orbitals that can exist in the 4th. Yep. I can have a 4s. I can have a 4p. I can have a 4d. And I will have a 4f. Right? Because that's going to be the next one. How many electrons can go in these things? How many electrons can go into the 4s? In other words, how many 4s orbitals are there? And then 2 electrons can go in each one. So how many can go in all of the 4s? If I add them all up. Tyson, what do you got? Yep, 2 electrons. How many electrons can I put in the 4p orbitals? All of them. All of the orbitals loaded right full. How many electrons can go in there? Kristen? Sorry? 6. The p orbitals always hold 6. How many can go in the 4d? Yep. 10. The d's always hold 10 electrons. How many can go in the 4f? It's exciting. No, we're gonna wait. We're waiting for rookies on this. Who got? Ben, what do you got? 14. So how many electrons can go in the 4th energy level? Yep. Is it 32? 32 electrons. Okay? All right? 915, which is a good place to be. Now, at this point, don't write it down. This note was made by a previous chemistry teacher. You know how my notes are kind of wordy. I'm more of a picture type person. This is a complete summary of exactly what we've just done. I don't think it's worth writing down the entire thing, but it's online if you want to go back and look at it. If you're more of a wordy type, memorized type person, then this is a good thing. It tells us that electrons are located in energy levels, or shells, right? Energy levels are identified by the principal quantum number. N can be from 1 to infinity. N corresponds to the period number. N describes the size of the energy level. All right, we'll talk about that. So then energy levels are divided into sub-levels, the secondary quantum number, right? If in the first energy level, I only have a 1s. In the second energy level, I have a 2s and a 2p. In the third energy level, I have a 3s, 3p, 3d. In the fourth energy level, 4s, 4p, 4d, 4f. We just talked about that. Notice there's no such thing as a 1p, all right? Or there's no such thing as a 2d. So some quantum numbers, they just don't exist. The mathematical equation doesn't work for those particular values, and therefore we assume they don't exist, all right? And well, anyway, we'll talk about how this whole idea is supported by the shape of the periodic table. That'll be tomorrow. Sub-levels are divided into their orbitals. Each sublevel contains a certain number of orbitals, right? 1, 3, 5, 7. There's only one S-type, there is 3 P-type, there is 5 D-type, and there are 7 F-types. And each one can hold 2 electrons, so you can put 2 in the S sublevel, you can put 6 in the P sublevel, you can put 10 in the D sublevel, and you can put 14 in the F sublevel. Again, very repetitive to what we just did. Each orbital is associated with a particular size and 3-dimensional shape, and we've seen that already a little bit, and we're only going to be worried about really the S and the P shapes, and we'll get into that more when we start drawing atoms and drawing molecules. There's some homework concerning quantum numbers, and I also have a little worksheet, and I could probably get away from this worksheet, and that's because the new textbook, and I'm pretty sure those are new textbook numbers, I hope they are, because the new textbook has a little more questions on quantum numbers than the old one did, so I still have this extra sheet that you can do. Now, I am going to tell you 1, 2, 3, 4, 5. 1, 2, 3, 4. So today's lesson was obviously just defining the spaces that you can find these electrons. Tomorrow we're going to talk about filling the atom scaffolding that we just built with electrons. And then over the next day or two, I can't remember exactly what it is, we're going to talk about something called electron configuration, all right, and energy level diagrams. And then I'm going to give you a quiz. All right, and it's one of these biggish, medium, half a class quizzes, all right? And it's going to be just on the quantum numbers and the way we express it, because once we get into talking about atoms, and then we've got quite a long trek before we get to a test. I don't know what the date will be, but this lesson with about 3 more other lessons will then be ready for a quiz. It won't be happening Friday, I don't think, but it might happen on Monday of next week, that type of thing. And it's one where I just need to test you on these quantum number things, and then we can, once we use them and we're into using the letter designations, I don't want you to worry so much about the quantum numbers. Really, they don't have as much meaning as them just defining the orbitals. Once we've got the orbitals in our minds, we want to just kind of put that on the back burner and not worry about it so much. So that's the way that's going to work. All right, I am done.